Good day, everyone. This is Professor Friday coming at you one more time. Today we're going to be taking a look at an example of a surface area of revolution. What we're going to do is take a portion of the parabola y squared is equal to x plus 1, defined on the interval 0 to 3 for x, and we're going to rotate that about the x-axis. So first and foremost, I want to get an idea of what this thing actually looks like. Because of the x plus 1 and the fact that nothing is added or subtracted from the y variable, it is safe to assume that this thing has a vertex over here at -1, 0, and it will open to the right due to the fact that the y squared is positive and the x is positive. So we'll get a parabola that looks approximately like this. Not entirely accurate because I'm not a very talented artist, but that's okay. Now, the portion of the graph that we're supposed to be looking at is the portion from 0 to 3. Now, I noticed that on 0 to 3 we actually have two different things that are defined up here. One being the top half of the parabola, the other being the bottom half of the parabola. Now, it is safe to assume that because we're rotating this about the x-axis, that we don't need to use both halves of the parabola. What we get from sweeping one of them around the x-axis will actually sweep out the same region that the other half of the parabola will as well. So what we're going to do is just assume that we are talking about the top half of the parabola. It's not going to have a lot of impact on one of the methods that we use to set this up, but it'll have a bit of an impact on the other method that we use. So we're actually going to do this problem two different ways. The first way is we are going to parameterize with respect to x. That is to say, we were given x values up here, so it would probably make a lot of sense for us to parameterize in terms of x. Now, first thing we're going to have to do, if we're going to parameterize with respect to x, is actually make sure that we have y as a function of x. Currently, it's implicitly defined. What we're going to do is define it explicitly. Now, we could do so by taking the square root of both sides, which would give us y equals plus or minus the square root of x plus 1. The significance of the plus or minus, plus refers to the top half of the parabola, minus refers to the bottom half of the parabola. Again, we only need the top, so we'll point that out. Only need top. So we'll just be making use of the positive square root of x plus 1. Now, the formula that we have for surface area of revolution, capital S, is equal to definite integral from limit to limit of a circumference times ds. Now, r refers to the distance from axis of rotation to whatever our function is. Now, the axis of rotation in this case is the x-axis, which means that the distance from the axis of rotation to the actual region is going to be our vertical variable. So in this case, that would be y. So as we set this up, this is going to be the definite integral from 0 to 3 of 2 times pi times y times ds. Now, ds comes from our arc length formula, and if we are going to parameterize this in terms of x, it'll get the following parameterization. This will be 1 plus the derivative of y with respect to x, quantity squared, dx. This comes to us directly from the Pythagorean theorem. So, with that in mind, let's see if we can do all those things. We have y is equal to the square root of x plus 1. For purposes of the power rule, let's go ahead and call that x plus 1 raised to the 1/2 power. We differentiate. According to the power and chain rules, this would be 1/2 times x plus 1 to the -1/2 power, or 1 over 2 square roots of x plus 1. According to our formula for ds, next thing we're going to want to do is square this. Squaring it will effectively cancel out the square root, but we'll also need to square the 2 in the denominator. So this will give us 1 over 4 times the quantity, x plus 1, or 1 over 4x plus 4. Looking good so far. Next thing I'd like to do is add 1 to this. We'll say 1 plus dy over dx quantity squared. This will be equal to 1 plus 1 over 4x plus 4. Getting a common denominator for these, we can call this 4x plus 4 over 4x plus 4 plus 1 over 4x plus 4. Combining these to a single fraction, we got ourselves 4x plus 5 over the square root, or not the square root, sorry, that's next step. Sorry, getting ahead of myself. It's wild and crazy right now. Alright, so with this in mind, the next step for calculating ds would be for us to go ahead and take a square root of that whole thing. So, put this up here. And, oh boy. Alright, well, that didn't work at all. Copying from the last page, we now have that the square root of 1 plus dy over dx quantity squared is equal to the square root of 4x plus 5 over 4x plus 4. Now what we're going to do with this is the exact same algebra that got us to this denominator in the first place, which is that we are going to recognize that the denominator has the greatest common factor of 4 and can be factored out. Now because of that, I'd like to take the square root of that 4 and call this 1/2 times the square root of 4x plus 5 over x plus 1. The 4 came from the denominator, so the 2 is going to remain in the denominator, which is why we have the 1/2. So this basically sets up our expression for ds, and we are ready to evaluate. So s is going to be equal to, limits of integration were given to us in the problem. This will be from 0 to 3. We have 2 times pi times y. And now we have an expression that we can plug in for ds. This is 1/2 of the square root of 4x plus 5 over x plus 1. Hi, baby. Times dx. My very vocal cat has come to join us. So with this in mind, I notice that we are trying to parameterize this with respect to x, and yet we have a y in here. So what we're going to do is do a little substitution and plug in what y was equal to in the first place, which was y equals the square root of x plus 1. In addition to that substitution, I'm going to take the 2 and the pi and the 1/2 and pull them all outside the integral. The good news is that the 2 and the 1/2 will cancel each other out. And we'll have a square root of x plus 1 times the square root of 4x plus 5 over x plus 1 times dx. A fantastic thing happens at this point, which is that we observe that the square root of x plus 1 and the square root of x plus 1 will effectively cancel each other out, giving us pi times the definite integral from 0 to 3 of the square root of 4x plus 5 dx. Evaluating this integral will be not nearly as bad as what brought us here. So let's see if we can handle this. We'll do a u substitution for this. U is equal to 4x plus 5. Therefore, du is equal to 4 times dx. Since I don't have a spare 4 lying around, I can do some algebra to call that excuse me, dx is equal to 1/4 of du. Then making the appropriate substitutions on the limits of integration, u of 0 is going to be equal to 5, and u of 3 is going to be equal to 4 times 3, which is 12 plus 5, we'll call that 17. So making these substitutions, we'll do the substitutions in purple. This will be 5 to 17 of the square root of u times 1/4 of du. The 1/4 can come join the pi on the outside. Joining pi on the outside, we'll call this pi over 4, and then we're going to integrate the square root of u. Like we did earlier, we'll get into the mindset of that is u to the 1/2 power. So we increase the power to 3/2 and divide by the new exponent. and that'll take us from 5 to 17. We can take the pi over 4 times 2 over 3, reduce the 2 over 4, call this pi over 6, and then plugging in our limits of integration, we'll get 17 to the 3/2 power minus 5 to the 3/2 power. Now, if you prefer, what we could also do with a 3/2 power like this is call this 17 square roots of 17 minus 5 square roots of 5, put that whole thing over 6. Now, we never had to substitute back due to the fact that this was a definite integral, so that worked out pretty well. Now, this is one strategy for the given problem. We started this off with the decision that we were going to parameterize with respect to x. It is possible to set this up by parameterizing with respect to y. I'd like to demonstrate what that looks like. So, restarting this one, we had y squared is equal to x plus 1. We had that x goes from 0 to 3, and we had that we were rotating about the x-axis. Now with this in mind, let's see, what did I call it last time? I called it 1 last time, so for 2, we're going to parameterize with respect to y. Now, parameterizing with respect to y means that we need to do a couple things. First one is take the original function and solve for x. Solving for x this time does not involve a square root. It simply involves subtracting 1 from both sides. Now we have x as a function of y. The other thing that we'll need to do is worry about our limits of integration by setting x equal to 0 and by setting x equal to 3. So for x equals 0, we wind up getting that y squared is equal to 1, which tells us that y is equal to, now normally it would be plus or minus 1, but because we've already made the decision to only talk about the top half of the parabola, that's what takes us to the fact that it'll only be positive 1. And we'll have y squared is equal to 4, which leads us to y is equal to 2. So limits of integration for this integral will be from 1 to 2. Now if we are going to go with respect to y, then we will need to set up ds, this time as the square root of 1 plus the derivative of x with respect to y, quantity squared, times dy. So using this guy right here, let's start the order of operations. So first thing is take a derivative. Dx dy is going to be equal to 2y, which we will then square. 2y quantity squared gives us 4y squared. Adding 1 and taking a square root is going to give us something that I recognize that we cannot simplify in its current form. So we'll just go ahead and call that 1 plus 4y squared dy. So this is what our expression for ds will be this time. We said earlier that the surface area is going to be the definite integral from limit to limit of 2 pi y times ds. We can now set up what this looks like. So in terms of y, this was the definite integral from 1 to 2 of 2 times pi times y times 1 plus 4y squared dy. There's a big change that has happened this time that is definitely noteworthy, which is the fact that I don't need to make a substitution on y. This is due to the fact that we're already set up with respect to y. On the last example, when it was set up with respect to x, we needed to make a substitution on y. So the combination of whether you're rotating about the x-axis or the y-axis, combined with am I parameterizing with respect to x or y, will allow you to make the determination, do I need to make a substitution here? In this case, the answer is no. Instead, we can proceed to integrate. Now, given the 1 plus 4y squared under the radical, you might be tempted to think trigonometric substitution, and let me tell you, you're not wrong. However, we can make this problem a lot easier by doing simply a u substitution. The u substitution I'd like to do is 1 plus 4y squared That way we'll have that du is equal to 8y dy. Now, I don't have a spare 8y dy lying around, but I do have a 2y dy lying around. So I'm going to borrow this 2, this y, and this dy, and dividing both sides by 4 will let me know what that's equal to. So that 2y dy will become 1/4 du in the next step. We also need to know what our limits of integration will be after substituting. So at y equals 1, u would be equal to 1 plus 4 times 1 squared, which is 5. And at y equals 2, we'll get u is equal to 1 plus 4 times 2 squared, which is 17. By an amazing coincidence, 17 and 5 were the two numbers that we saw last time we did this problem. So, setting this all up, we'll have, we can pull that pi outside of the integral since it is a constant multiple. Definite integral from 5 to 17 of the 2y dy, that all will become 1/4 of du, and we are left with the square root of u. It is not a coincidence that the integral that results is precisely the exact same integral that we got from our last method. Now, if you want to reference back, our final answer for this one was pi times 17 square roots of 7 minus 5 square roots of 5 all over 6. That came as a result of doing the power rule followed by plugging in the limits of integration. I hope that this was enlightening for you, and I'll see you all on the next video.